Question 3, physics higher paper, combined science. Question 3A, part 1, just asks you to draw the field lines. Now remember, the rules for drawing the field lines, they always go from north to south, magnetic field lines north to south, so just wherever you see that, make sure you do that. Now, going out from the north and going into the south. Okay. Now the rules for field lines as well is the closer they are together, the stronger the field. So we could have put an X here or here for part 2. The strongest field is at the ends. So describe the differences between the magnetic field shown and a uniform magnetic field. So uniform magnetic field, one direction. The north-south is the different directions. The lines are straight. They're parallel. They're equidistant, just means the same distance apart all the time, and the same strength, same field strength everywhere. Same field strength everywhere. So that's just repeating your rules for drawing field lines, and recognise that uniform just means the same. So when you're uniform at school, everyone looks the same, don't they? Yeah, that's what the idea of it is. Everything's the same. Now in a laboratory, remember we could have had a solenoid. Solenoid is just a collar wire with a current flowing through it. Okay, now remember, outside it's like a bar magnet. Yeah, outside like a bar magnet. But inside, you get these beautiful straight lines, all equidistant, yeah, going the opposite direction to the outside, and that's your uniform field in there. You would also got marks if you'd said a couple of magnets opposing each other with north and south facing, because that would do the same thing. Okay, also got marks for a horseshoe magnet, because that would give you a north and south. Okay, marks for either of those things. Okay, now, next thing we need to look at is the Earth's magnetic field. Remember, we have compasses. Compasses always point to the north, right? So a north always points to a south. So the Earth's magnetic field must be a south pole. So they're kind of the opposite here. So what we're looking at is you're just drawing little arrows coming in here like that. Little arrow on there like that. Little arrow coming in. Little arrow coming in. Little arrow coming in. So that one you could have drawn like that, through there, through there, through there. Now extend it in a little bit just to show them coming through the earth. Didn't need to worry about the direction inside the field. And so it's something like that where you've got coming away from the north. Yeah? Okay. And into the south. Just the same as before. So you've got the south. So just imagine these are magnets, you're pointing into the south. So the Earth's north pole, we call it the north, is actually magnetic south. That's what that was testing there. Okay, now the outer core, because we've got a solid inner core, it's the outer core that causes it. I gave you the centre, but if you get this in the real exam, you must say the core. I gave you, if you said the centre, I was being generous, but you must say the core. It's the core, not the centre. So make sure you say the core. Okay, next one is rearranging the equation for B. So we just divide both sides by I and L. So we get B equals F over I times L. Then we're going to substitute 1.11 times 10 to the minus 5. Most people are quite good with their standard form. However, careful here, milliamps, right? Whenever we see that, replace the milli with 10 to the minus 3. So this one would become 93.1 times 10 to the minus 3 amps. And then on the bottom, what times the length? The length is in meters, which is perfect. Yeah, meters, lovely. Okay, evaluate that all out, comes to, rounds to 2.0 times 10 to the minus 4. Lots of people got marks for that, but it's a power of 10 wrong. You lost a mark. So it's just that milliamps. Yeah, make sure you know the difference between, so the ones we need to know for GCSE, certainly physics, milli, micro, nano, and then going up we've got kilo, mega, giga. Yeah? So whenever you see that, just replace it 10 to the 9, 10 to the 6, 10 to the 3, 10 to the minus 3, 10 to the minus 6, 10 to the minus 9. So just take the n out, the m out, that's a little mu, yeah? Take those out and then replace it with those standard forms. Most of you can do your standard form really well. Okay. So, gravitational field strength. So he was just selecting an equation, mgh, yeah? So, change in GPE equals, change in gravity even tells you what to do. M times G times the change in the height. Plug in those numbers, 1100 times 3.7 times 1.8, again 1.8 kilometres, kilos 10 to the 3 times 10 to the 3 metres, multiplying it all together gives us 7,300,000 joules. Okay, now again, same numbers here, change in kinetic energy. So delta KE equals a half mv squared. Didn't need to rearrange it, it was just substituting. So it's a half times the mass, which was 1100, times 88. And lots of people forgot the squared. How frustrating is that? Evaluate that out, it comes to 4,300,000 joules. Okay. So next question. Ask what it's a described question, so we're good with described questions because we just say what we see, right? But we had to talk about terms of work done by forces. Remember, work done equals force times the distance. So we had to talk about energy changes in terms of work done. Okay, so first I could say work done against gravity. Yeah, because we're not doing work against gravity, it's going to speed up. And it's by the jets. Yeah, work done against gravity by the jets. So 2 marks there. Okay. Work done against air resistance by the parachute. Okay. Reducing the kinetic energy store. Yeah? So the parachute reduces the kinetic energy store. As we go down, as we descend, GPE decreases. Yeah? Also there's chemical energy change from fuel, and all of this energy ends up as thermal energy in the environment. Okay, okay. And the transfer path was mechanically, just in case you got that as well. Not many people did, to be fair. Okay, so next one, show that. Show that means that you can't use that number, yeah? Can't use the final answer. So we have to do it using the other stuff. Lots of people did 2.16, divide it by that and got that. You have to go the other way around, yeah? So show that it can provide that. That's the answer. So the answer to this question could be, what is the energy the solar panels can provide? But here it's showing what the energy you can. So energy equals power times time. And then to get the marks, you have to see this. 1200 times 30 times 60, 30 minutes times 60. And that was it. So we had to see that. So to get the mark, you had to show that calculation. Okay. Now, next one's an efficiency question. Write down the equation. Efficiency equals useful out over total in. Yeah? So rearrange, we're trying to find the solar energy received, so that's the total in. So total in equals useful out over efficiency. Now efficiency is given percentage, so write it as a decimal, 0.27. Okay, so substitute in, total in equals useful out, which was 2.16. Remember, mega times 10 to the 6. 10 to the 6 divided by percentage, 0.27, and the answer to that is 8.0 times 10 to the 6 joules, working backwards. It's like a reverse percentage. Okay, well done. And now moving on to question 5, sorry.